listen-only mode.
Lane highways. This morning's session will consist of 3 modules: an introduction on substantive safety and the Highway Safety Manual, followed by a session on undivided multi-lane rural highways, models, and crash modification factors. And the third session of this morning's webinar will be on rural divided multi-lane highways, the models, and the appropriate crash modification factors. In getting started this morning, I'd like to call your attention in the upper right of your screen and ask you to participate in the poll by identifying how many people are in the room with you today on your call-in line. It's always sort of a mystery to us in presenting webinars as to just how many people we're reaching. We know how many call-in lines there are, but it's really hard to, without your help, to identify how many people we're actually reaching. I'd ask you to participate in the poll if you can, and indicate how many people are in the room with you. Also in the opening screen on the right-hand side is the Highway Safety Manual Webinar Series presentations. Today's 3 sessions, 1, 2, and 3 on multi-lane rural highways are the first entries you can see. You can download these at the end of today's webinar. They're in PDF form for you to use until you receive, if you have not already, your copy of the printed Highway Safety Manual. With that, I'm going to move to the presentation room, and we'll get started with today's webinar. In regard to a question that came in, if there would be professional development hours awarded for the webinars, we're unable to do that at this point in time. That's another step in the evolution of webinars conducted by FHWA. And I'm awaiting for this first session to get started. I am aware, and as Gene Apparano, who's our other presenter today, is that many people who have placed orders for the Highway Safety Manual are now receiving the printed copies. If you gotten yours, be happy. You know that they're shipping and shipping and shipping them from AASHTO, and if you've already ordered your copy, it'll soon be in your hands. Session 1 will be introduction and background information on multi-lane rural highways. Our 2 presenters today are myself, Fred Rank, from FHWA's Resource Center, and the other one will be Gene Apparano, who will be giving the following session to this introduction session. Gene will be presenting on undivided rural multi-lane highways. Our learning outcomes for the first module are to review the crash frequency safety performance of rural multi-lane highways and to define for you substantive safety, which is a concept that goes beyond nominal safety as we've always thought of it. Gene, could you please advance the slides and tell me which one you're advanced to? If you go to slide 5.
We're on slide 5.
Okay, slide 5. I was experiencing a real slow internet connection. My apologies to the use of those of you on the webinar. Multi-lane highways are a very small portion, less than 1 out of every 5 miles of U.S. highways. They constitute the small amount of the U.S. federal aid mileage, not a large share at all.
Fred?
Yes, I'm bringing up, I'm with Gene. I've totally lost the internet connection here, so I'm going to call on you to advance the slides as soon as I can get up and see them in my hand here.
Just say next and I'll advance the slide.
Sure. Yes, if you would go to slide 6.
There.
Okay. Slide 6 is the mileage by the number of states for multi-lane rural highway mileage. Yeah, as you can see, Texas has the most miles of multi-lane rural highway, followed by Virginia, New Mexico, Mississippi, Ohio, Missouri, and Georgia comes in number 10th. There are other states that have mileage, but they don't have the numbers of miles that Texas and Virginia, New Mexico, Mississippi have. If you go to slide 7, Gene, the fatality rates on rural federal aid primary highways are significantly higher than urban and rural interstate freeways. And this is something for you to keep in mind in terms of the performance, say in terms of crash frequency for rural multi-lane highways. If you go to slide 8, the crash rate on rural expressways is less than that for rural 2-lane highways. And this is an important thing to keep in mind for those states, those agencies that are looking at converting rural 2-lane highways to multi-lane rural highways. Go to slide 9. The severity on rural expressways is less than for rural 2-lane highways. So even though it's a divided multi-lane, they're still, for the most part, safety-wise across the country, better than 2-lane roads overall. When access density is low, crash rate is similar to a rural freeway. If you go to slide 9.
We're on slide 9. We're on 10.
Hang on. Slide 10. In fact, a comparison that came out of NCHRP 650 in terms of crash rates, the column in the middle for crash rates, 324 miles of rural 2-lane highways planned for expressway conversion from Nebraska, in comparison to 111 miles of rural 4-lane divided expressways. Overall, fatal fatalities were 31.8% lower, injuries were lower, but property damage crashes were slightly larger. And this is to keep things in perspective so you understand how things fit in relationship to the performance of other roadways. Slide 11, please. Our knowledge as engineers and transportation professionals remains imprecise. Judgment's essential. Meeting the standard of your design standards or the MUTCD does not necessarily make a highway safe. Some important features of highways are not determined by standards, such as the spacing of interchanges or intersections, for J-turns, angled positive offset left turn lanes. All of these things are not typically found in our national standards. Next slide. On the left-hand side, we've typically thought in the past, up until about the mid-1990s, of safety being in terms of complying, meeting the minimum requirements of our design standards for such things as vertical curvature, horizontal curvature, for cross slope, super elevation, length of tangents, and tapers. And as long as we met those, a road was thought of as being nominally safe, in other words, safe in name only. Since the mid-1990s, a different way that looks at safety and crash frequency performance in a more progressive manner has evolved, and we call this substantive safety. And substantive safety is the expected or actual crash frequency or severity for a piece of roadway or highway. You go to slide 13. Nominal safety is a first step, and it's based on research and our past experience in the United States and what has built our design standards to be what they are today. And I'd like you to think of it as a first step. Do you meet the minimum values? Do you comply with the minimum requirements of your design standards? Go to slide 14. In the first step, nominal safety, and looking at this divided 4-lane piece of highway in Missouri, US 54. We have 12-foot lanes, 8-foot gravel shoulders, and we would typically think of this as meeting all the nominal requirements for lane width and shoulder width. In the second step, substantive safety, we pave the shoulder, but more importantly, we add a rumble, longitudinal rumble along the side of it. And rumble has a known crash frequency reduction associated with it of about 16% fewer crashes. Going beyond nominal, such as installing a longitudinal rumble, can reduce crash frequency. Slide 15. The new Highway Safety Manual of 2010 has a methodology a lot like that that was for the Highway Capacity Manual. And the Highway Capacity Manual is a set of analysis tools that allows us to evaluate the safety performance, or that is the crash frequency performance for a piece of roadway. The Highway Safety Manual will allow us to make informed decisions in terms of what types of designs will result in differing crash frequencies. It allows for more balanced decision making. Go to slide 16. What the Highway Safety Manual is it's a set of analysis tools. And that is all it is. It describes the mathematical relationships for safety performance based on exposure and roadway conditions. It does not have standards. It is not a best practice guidance document. The HSM does not supersede other publications that do. It is not like the MUTCD nor the Green Book. The MUTCD contains standards as well as guidance and options. The Green Book has only 4 standard requirements or shall requirements, and the remainder of it is guidance in terms of design of a facility. Slide 17. So the Highway Safety Manual is a set of tools for the prediction of crash frequency and for the analysis of safety. It facilitates explicit consideration of safety throughout any project development process. The Highway Safety Manual is a compilation, a synthesis of the validated highway safety research of all of the studies and all of the information that's available to you, the transportation professional. It provides analytical tools to predict the impact of decisions on road safety. Slide 18. So the Highway Safety Manual contains the best of the known science of safety and research. Slide 19. We have for some time been able to evaluate and quantify environmental impacts such as number of acres of wetlands disturbed. Operationally, we can compute levels of service and total delay for an intersection project. We can certainly do the economic analysis on costs and benefits, but what we haven't been able to do until the advent of the Highway Safety Manual is to be able to quantify safety performance. Slide 20. So quantifying safety for crash prediction, how can we use it? We can use it at the program level to prioritize segments or locations. We can use it at the project level to assess relative needs within a project. Is safety an issue? How big of an issue? We can communicate the relative needs in terms of crash frequency performance to the public, and it provides an excellent way of the supporting documentation for design exceptions. You could even use the Highway Safety Manual to a certain degree in terms of tort defense, and that's been envisioned and discussed for some time by AASHTO in developing the Highway Safety Manual. You can use it to quantify the relative safety of the facility and demonstrate that an agency is addressing safety needs adequately. Slide 21. FHWA has made it a policy, a program memorandum, in the form of a program memorandum, that safety be fully considered in every aspect of planning, programming, environmental analysis, project design, construction, maintenance, and FHWA acted to do that back in January of 2005. So the methods, the methodology, the results of the Highway Safety Manual should be incorporated into the work of your agency as you develop a project and make decisions into a project. If you're applying for federal aid funding for your project or have federal aid involved in some aspect of your project, please be advised that it is the policy of FHWA that you fully consider safety. And in terms of that, what that means is to use the methodology, to use the proven analysis techniques of the Highway Safety Manual to quantify it. Slide 22 is balancing safety with many other factors is critical to good design decision making. With being able to quantify safety on the right, we can now bring it into the balance of how decisions are made overall in the project. The role of road design and crash prevention, slide 23. Design can reduce the incidence of human error. Humans will always continue to err in the driving process. The human brain's a parallel processor, and inherent in parallel processors is branching to not the same decision reliably all of the time. We know that drivers make mistakes. They continue to do them, and those errors sometimes result in a crash. How we design a facility and operate it affect, will that error on the part of the human being in the driving task result in a crash, and how severe that crash will be. So what can the Highway Safety Manual do for me? Slide 24. You can use it to predict the safety performance of geometric design features such as shoulder width, side slope, access. You can use it to quantitatively calculate safety effects. You can use it to predict safety performance for intersections in terms of crash frequency and the effects of countermeasures. You can use it for better decisions for safety. And that's what we're seeking with the Highway Safety Manual and its deployment. Slide 25. We reviewed the crash frequency, that is the safety performance for rural multi-lane highways, and briefly covered the new term, subsidy safety, which goes well beyond previous thinking, which we'll identify as nominal safety. And with that, I'll turn the webinar over to Gene Appareno, who will conduct the next session.
Thank you, Fred. You want to advance the slides for me? Okay, I was just teasing you, Fred. This next module, we're going to be talking about the HSM methodology for predicting crash frequency for undivided rural multi-lane highways. We're going to describe the base models, or better known as the safety performance functions, that are used to calculate this predicted crash frequency. We're also going to describe and look at the crash modification factors associated with rural undivided multi-lane highways. And we're going to show you through demonstration on how to apply the crash modification factors. First, we want to define what a rural multi-lane highway is. Rural is defined as locations outside the boundaries of urban areas where the population is less than 5,000 persons or inhabitants. Any highway that's located outside the city limits of an urban habitat area above 5,000 inhabitants is considered a rural area. And it can be a little bit challenging to differentiate between urban and suburban areas in some areas, but usually they're on the outskirts of urban habitat areas. Multi-lane facilities usually have 4 or more lanes with a continuous cross-section. They may be divided or undivided. They could have a rigid barrier or flexible barrier, or they could just have a paved or a landscape medium. They should not have access or egress that's limited by grade-separated interchanges. That mean that they should not be freeways, but occasional grade-separated interchanges are acceptable as long as they're not the primary form of access. There are some limitations on the methodology. The Highway Safety Manual covers a lot of geometric and traffic control features, but not all. As you go through your copy of the Highway Safety Manual, once you get it, you will see that there are some areas that are lacking, that are not addressed with a crash modification factor. But the Highway Safety Manual is a living document, similar to what the MUTCD is and the Highway Capacity Manual. And as research advances, there will be more crash modification factors that come on board to be included in future editions of the Highway Safety Manual. But for now, we have some limitations. It only includes geometric design elements whose relationship to safety are well understood and where there's enough research data available to determine those crash modification factors. It treats the effects of individual geometric design elements and traffic control features as independent of each other, and it ignores any potential interaction between them. The crash prediction methodology consists of 18 steps. This happens to be figure 11-1 out of the Highway Safety Manual. And basically what we're going to discuss today are steps 9 and 10. We're going to assume that steps 1 through 7 have already been completed, which means defining the roadway limits, defining the study period, determining your traffic volumes and your actual geometric conditions, and observing the data. We're assuming that that's already taken place. And then the following steps after steps 9 and 10 has to deal with calibration. There is a calibration sequence in Appendix C of the Highway Safety Manual that walks you step by step on how to calibrate. If you happen to be on the able to participate in the first webinar on June 14th, we did show a demonstration, or not a demonstration, but the process that's used for calibration, and a copy of that presentation is available at the conclusion of today's webinar. Then the remaining of the steps is just a repeating some of the other steps if you are considering another year, another site, and then the final part is putting it all together where you sum up all your crash frequencies from various sites. But today we're going to be focusing on steps 9 and 10, which is applying the safety performance functions and also applying the crash modification factors to a rural multi-lane highway. The SPF models, or safety performance functions, are used for predicting the total accident frequency on a roadway segment. The prediction is determined in crashes per year. They're based on a set of nominal baseline conditions for geometric design and traffic control elements, such as for lane width, the base condition would be 12-foot lane width, and for shoulder width, it would be 6-foot shoulder width on undivided segments and 8-foot shoulder width on divided segments. SPF values, or the estimates, are adjusted by the crash modification factors that represent the safety effects of individual geometric design and traffic control elements that differ from the baseline conditions. First thing we have to do in order to analyze a segment of roadway is to divide it into homogeneous highway segments and also into intersections. Intersections will be covered in a webinar next week for multi-lane, rural multi-lane intersections, that is. We covered next week on July 13th. So if you're available, you can sit in on that presentation. But today we're going to be covering highway segments. The definition of a highway segment can occur anywhere along a roadway, but if it happens to be between two intersections, then the segment should begin and end at the center of each of those intersections. There's also a way to distinguish crashes with respect to roadways. They can be determined by the physical limits of the intersection, such as the curve radii or the crosswalk limits, where all those crashes that occur in Area A would be considered intersection-related crashes, and areas outside Segment A, which are Segment B, would be considered segment-related crashes. Some states have a policy where they give a specific distance from the center of the intersection to designate intersection-related crashes. For example, some states will say specify 200 or 250 feet from the center of the intersection to be classified as intersection-related crashes. Segments, the portions of the facility delimited by major intersections, significant changes in the roadway cross sections, geometric characteristics of the facility, or surrounding land use. So anytime there's a change in any of these conditions, then you would want to break it out into a separate segment. Again, roadway segments can be divided or undivided. And these are the segments that these are the roadway characteristics that you would look to divide your segments up into. It'd be based on your traffic volume and vehicles per day, your lane width, your shoulder width, and also your shoulder type, the type of side slopes that you have, whether or not you have a median presence, and also if you have major intersections. You would want to segment the roadway portion between major intersections. To account for variability in lane width, shoulder width, and median width, a range of widths have been used to assign what we call a rounded value to be used for a final determination of what lane width you would want to use. For example, if you had a lane width of 9.7 feet, then you would round that down to 9.5. If you had a lane width of 9.3, then you'd round it up to 9.5. This is just meant to account for the variability that actually takes place out in the field. They have a similar process for shoulder widths. If your shoulder falls within a particular range of values, then you would round it up to the particular rounded shoulder width shown on the right. For median, they also have a range of median widths where you would also round up to a particular median width. These are some of the cross-sectional elements that we will be looking at that affect safety on multi-lane highways. Well, lane width, shoulder width, and side slope. And there's crash modification factors for each of these, and we'll discuss each of those. But to determine a crash frequency, it's basically a three-step process. You predict the number of total segment crashes per year. You predict the number of crashes that occur in roadway segments. Then you predict the number of total crashes that occur for your intersections in your roadway segment. And then it's just a matter of combining those two predictions to come up with a total predicted number of crashes. The SPF, Safety Performance Function base models, they apply or address two types of roadway segments for rural multi-lane highways. They're undivided and divided roadways. The models themselves are the same for divided and undivided highways, but the regression coefficients differ between undivided and divided highways. And this is the safety performance function for rural multi-lane segments, where you have 4 variables. The length of the roadway segment is in miles. The AADT is the annual average daily traffic and vehicles per day. And then you have your A and B regression coefficients. And they differ between divided and undivided. The process for predicting crashes for divided or undivided remain the same. You apply the safety performance function, then you apply the appropriate crash modification factors and a calibration factor if you so choose. Now we're going to get into the undivided rural multi-lane roadway segment, and we're going to look at the safety performance function and the A and B regression coefficients. The A regression coefficient for total crashes, 4-lane total crashes, is minus 9.653, and for B it's 1.176. These are from table 11.3 out of the Highway Safety Manual. Now, if you wanted, you could use the coefficients below if you wanted to just look at fatal and injury predictions, or if you wanted to look at fatal injury predictions that exclude possible injuries. So there's a couple ways that you can come up with a prediction. It could be total crashes, it could be fatal and injury crashes, or fatal and injury crashes excluding those that are just considered possible injuries. And with that safety performance function, as we stated earlier, there are base conditions, and those base conditions are that we're assuming that we have a lane width of 12 feet, shoulder width of 6 feet. We're assuming that our shoulder type is paved. Our side slopes are 1 to 7 or flatter. And we're also assuming that there's no lighting or automated speed enforcement present along the particular roadway segment that we're analyzing. This is default distribution of crashes by collision type. If you wanted to, you could use these collision type totals that's in the left column. For example, head-on crashes of 0.009 or about 1%, side swipes about 1%, rear-end crashes is about 25%. If you wanted to estimate the collision type, you could use these percentages to calculate or multiply to your predicted value to come up with what you would expect to be the number of head-on crashes or side swipe crashes or rear-end crashes or angle crashes. And these are default values only that are in the Highway Safety Manual. If you have your own percentages with local data, then the Highway Safety Manual recommends that you replace these default values with your actual values to come up with a more reliable estimate of collision types. I'm going to walk through an example. We're assuming we have a multi-lane rural undivided highway. Our traffic volume is 18,000 vehicles per day. Our segment length that we're looking at is 8 miles. Our lane width is 11 feet. We have an outside shoulder width of 8 foot, and it's paved. And we have side slopes of 1 to 6. But first, we're just going to look at applying the safety performance function for base conditions. And we're going to be looking at total crashes. So we pick the A and B coefficients for total crashes, which is the minus 9.653 and the 1.76. And then we substitute in our values for traffic volume, 18,000 vehicles per day, and our project length, which is 8 miles. Putting those values in is an exponential calculation. We come up with an estimate of 51.9 crashes per year for that 8-mile segment of roadway. Now to come up with our total predicted number of crashes, we have to make an adjustment from our SPF value for base conditions, and we use the crash modification factors that adjust our predicted SPF value to either existing or proposed conditions that can be before or after a particular safety improvement. These are the crash modification factors for undivided roadway segments, table 11-10 out of the Highway Safety Manual. There are 5 primary crash modification factors. The first is for lane width. The second is for shoulder width and shoulder type. Third is for side slopes. Fourth is for lighting. And the fifth is for automated speed enforcement. And there are some other crash modification factors in Part D of the Highway Safety Manual. This is in Part C. But we will show you what some of those are at the end of this presentation. And you also, if you notice in the far right column, they also provide the equation numbers and the exhibits and table numbers where you can find those crash modification factors. Okay. I'm experiencing difficulty here myself. Our next example is we're looking at the CMF for lane width for an undivided rural multi-lane roadway. The example is that we're using an 11-foot lane with an ADT of 18,000 vehicles per day. So going to the far left of our table 1111, looking at 11-foot lane width, which the CMF RA is a function of traffic volume, and we're greater than 2,000 vehicles per day, so that our CMF RA for our lane width would be 1.04. So putting in the value for our CMF RA of 1.04 into our crash modification factor function, and performing the calculation, we come up with a crash modification factor for lane width of 1.011. The next CMF, or crash modification factor, is for shoulder width and shoulder type. There's 4 variables that are involved: CMF WRA, CMF, which is for shoulder width, CMF TRA, which is for shoulder type, which comes from table 1112 and 1113, and then the proportion of total crashes that's related to run-off-the-road crashes, and that is assigned a default value of 0.027. So, for example, if we had a shoulder width that was 8 foot or more in width, we had an ADT, or traffic volume of greater than 2,000 vehicles per day, our CMF WRA would be 0.87. It's paved, so our CMF for TRA subscript would be 1.0. Carrying those values over into this example calculation, we would select the particular values for the shoulder width out of table 1112 and for the shoulder type out of table 1113. And where you're looking at a 4-foot gravel shoulder. I thought we were looking at an 8-foot paved, but we're looking at a 4-foot gravel shoulder. Substituting those values in to our crash modification function, we come up with a crash modification factor for a 4-foot gravel shoulder on a roadway segment of 18,000 vehicles per day of 1.04. Something worth mentioning here is that if your crash modification factor is greater than 1.0, then that would lead you to expect an increase in crash frequency. So this 1.04 represents about a 4.4% estimated or predicted increase in crashes. That mainly has to deal with the shoulder width and the shoulder type. For side slopes, it's just there's no function, there's no calculations that need to be done or performed. It's just a matter of what you have. If it's 1 to 2 or steeper, you have a CMF of 1.18. For example, if you have a 1 to 5 side slope, then your crash modification factor is 1.09. And the base condition where the CMF or crash modification factor is equal to 1.0 is if you're at 1 to 7 or flatter. Our fourth crash modification factor is for lighting. It comes from table 1115, where we have the proportion of nighttime crashes for unlighted roadway segments. And these are default values. And the values are for 4-lane undivided. Our fatal injury piece of INR is 0.361. Our PDO piece of NR is 0.639. Our piece of NR is 0.255. And if you have your local data, a proportion of nighttime crashes, then these default values should be replaced with the local data that you have available. Base condition for automated speed enforcement is that it's not present, so your CMF 5RU for automated speed enforcement would be 1.0. But if you have automated speed enforcement present, then your CMF for injury crashes would be 0.083, but for total crashes, it'd be 0.095. Now we're going to try to demonstrate putting it all together where carrying forward our safety performance function from the previous calculation earlier where we had come up with a value of 51.9. We still have our roadway segment, 4-lane undivided rural highway, 18,000 vehicles per day. It's 8 miles in length. We have 11-foot lane width, 8-foot gravel shoulder, a side slope of 1 to 6, and we're assuming that there's no lighting or there's no automated speed enforcement. For lane width, from table 1111, our CMFRA would be 1.04. Putting that value into our CMF function for lane width, we calculate a CMF for a 11-foot lane as being 1.011. For an outside shoulder width of 8 feet, which is gravel, from table 1112, our CMF WRA for shoulder width is 0.87, which means that we would expect a reduction in crashes because our base value is 6 feet and we're at 8 feet. However, being our type of shoulder is gravel, our value from table 1113 for CMF TRA is 1.02, which is greater than 1. So we could expect about a 2% increase in crashes. Combining those two values together to calculate our final CMF for shoulder width and shoulder type, our value is 0.97. For a crash modification factor for a 1 to 6 side slope, going to table 11-4, we can see that the value for a 1 to 6 side slope is 1.05. Going to table 1115 for lighting, assuming there's no lighting, then our default value, our CMF, is 1.0. If automated speed enforcement that's not present, again, our CMF would be 1.0 for the base conditions. Then just putting it all together for the roadway segment are CMF for lane width, shoulder width, side slope, lighting, and speed enforcement. Those are crash modification factors 1 RU through crash modification factor 5 RU. And multiplying that times our SPF predicted value of 51.9, we'll come up with a total predicted number of crashes for that segment of 53.4 crashes per year. As I said earlier, there are some additional crash modification factors that are in Part D of the Highway Safety Manual. They have crash modification factors for flattening the side slopes along a roadway, for changing from one particular type of a barrier to a less rigid barrier, for installing a median barrier along a roadway segment, for using crash cushions at fixed objects, installing edge lines, center lines, and post-mounted delineators. There's also a crash modification factor for the use of shoulder rumble strips on rural multi-lane highways. That crash modification factor is 0.084, so it means you could expect a 16% fewer crashes on a segment that has shoulder rumble strips versus one that doesn't. What we did is we walked you through the process of using the safety performance function model to predict the crash frequency for an undivided rural multi-lane highway. We calculated the SPF value. We looked at the main crash modification factors that are in Part C of the Highway Safety Manual. We demonstrated application of those crash modification factors, and we also listed some of the other crash modification factors that are available in Part D. That concludes this session, and the next session will be Fred, where he will discuss the crash frequency method for divided rural multi-lane highways. Fred?
Thank you, Gene. If you could, Gene, there are two participants with their hands up in the attendee list, if you could see what they need. And I'll get started here with session 3 for divided rural multi-lane highways. Our outcomes for this session are to describe the models that predict crash frequency for divided rural multi-lane highways. And the models look the same, but the coefficients will be different. We'll calculate predicted crash frequency for divided example multi-lane highways. So you have case examples that you can refer to. We'll describe the appropriate crash modification factors for divided, and they do differ from undivided, even though they're rural multi-lane highways. And we'll apply them so you have examples that you could then double-check your work with. So slide 4. Before we apply them, you need to get organized and be logical and precise. One of the things about using the Highway Safety Manual is you need to be organized and be logical and think functionally in terms of how you organize the information, the material, and in particular, how you assign crashes to either the segments or to the intersections. Make sure your roadway segment that you're going to analyze is a homogeneous one in terms of ADT, lane width, shoulder type, side slope, presence of any median. Typically, we'll start a new analysis section where one of those values changes or at a major intersection. Again, for rounding, what if my measured width on a lane is only 11.8 feet? How do I use the Highway Safety Manual? And there are several tables available that you can make use of from Chapter 11 to round them up for a nominal value to use in the Highway Safety Manual equations. In the case of an 11.8 foot wide lane, you'd use 12 feet. For shoulder width, and then again, rounding, if the shoulder is 4.6 feet, then round it up to 5 feet as an example. And the same also with the presence of a median and median width. Please note that 25 to 34 foot wide medians are rounded to 30 foot for purposes of applying the Highway Safety Manual, and that the 30 foot median is our default or value that has no safety effect beyond the one that's included in the equations. Our equation, is to put it together, we're going to take the sum of our predicted crash frequencies, that is the predicted number of crashes for our road segments and for our intersections, and add them together for the entire project. First, we'll predict the total roadway segment crashes. Then we'll predict the number of intersection-related crashes for each intersection. And thirdly, we'll combine them using the equation at the top of the slide 3-8. Our model for rural multi-lane segments looks exactly the same as for undivided rural multi-lane. We have natural E, and we're raising it to a power of A plus B natural log of the ADT plus the natural log of the length in miles of our segment being analyzed. Looks the same, but what differs is the coefficients. So first we're going to apply the base model, and then we'll apply CMFs and any calibration factor. And we would do that with our safety performance function in sub SPF RU for road segment, our base model, and then apply any of the appropriate CMFs and a correction factor. So our equation is for the coefficients are from table 11-5, and for total crashes for 4-lane divided highways, our A coefficients of minus 9.025, our B coefficient is 1.049. I'm showing you also in a table 11.5 the different coefficients for fatal and injury crashes, and also fatal and injury crashes if you use the KABCO schedule. And that's included in the table 11-5. Our baseline conditions are 12-foot lanes, 6-foot wide shoulder. Now this is on a divided highway. If your state's standard width for shoulder on a divided rural multi-lane is 8 feet, then that would be the nominal value that you would assume for baseline conditions. Shoulder type is paved, 1 to 7 or flatter side slopes, no lighting, no automated speed enforcement. So for our example, 16,000 ADT, a segment that's 8 miles long, 11-foot lanes, 1 to 6 side slope. Outside shoulder width is 8 feet, but staggerate. Median width is 24 feet with no barrier, no lighting, no automated speed enforcement. So we would use the A and the B coefficients and plug them into our equation. And our predicted value is about 24.7 and something crashes. Now, at this point, I want to stop and ask and make sure you understand. The Highway Safety Manual reflects in a rigorous and quantitative way the relationships that you as a transportation professional have come to know in your work. The example that Gene provided in his session 02 was for the same 8.0 mile long segment at 16,000 ADT. And if you'll remember, the predicted number of crashes for this undivided was 45.17 crashes per year. Yet here, the segment we're looking at only differs by one thing. It's divided. And divided highways are inherently safer than undivided. And that's one of the principles of highway and transportation engineering. Guess what? Here in the Highway Safety Manual is the validation of that known relationship. And for the example of the length we picked and the ADT value of 16,000, it's rather dramatic that 45, instead of having 45.17 crashes per year predicted, we have 24.76 when we have a divided highway for the same ADT and for the same length. In fact, the Highway Safety Manual approach is fairly straightforward. The equations based on ADT to predict crash frequency are not like what we have with average crash rates that you may be compiling across a district of a state or statewide. And crash rates are a one rate, and I've shown in orange. The lines in black are the relationships of ADT to total crashes of the Highway Safety Manual for divided highways. For a site that has more crashes than the predicted value, such as we're looking at a difference here between the predicted value at 16,000 ADT to her total crashes, our segment that we looked at was 8 miles long. We predicted almost 25 crashes a year, 24.76. Divide by 8 is a little over 3 crashes per year, and you can clearly see at 16,000 ADT on the figure here, or the regression line for total equations. If, for example, we were experiencing 12 or 13 crashes per mile a year, that would be where the red X is. One of the values of the Highway Safety Manual is that with a fairly quick calculation, with a handheld calculator or with a spreadsheet, you can get a feel for what's the norm, where's the average through the middle of the data set, of these huge data sets assembled to develop the Highway Safety Manual, and my site that I'm looking at, my project, where's it in relationship to the middle of the data set, which is represented by the regression line, the black line for total crashes. That difference is, I'm going to just label it as difference in this case, but that's the amount of crash frequency that this site, with a higher number of crashes above the total crash regression line, that's where it's at. And you can clearly see from this example, this site is quite a ways away from the regression line and hence has a more acute safety need. As Gene provided to you for undivided highway segments in the previous session, Table 11-6 provides the default crashes, distribution of crashes by collision type. Each of these columns, the column for total, for fatal and injury, for PDO, add up to 100%. What's not provided in them is the relationship of total crashes to fatal and injury crashes to PDO. For example, for a divided highway, and in the right you'll see the picture, this is actually a photograph from Iowa that uses 8-foot gravel shoulders on their divided highways. 18,000 ADT, 8 miles long, 11-foot wide lanes, 8-foot shoulder but gravel, side slope 1 to 6, median and value width is 24 feet. A couple of things spring to mind. Our 11-foot lane is less than the assumed 12-foot default value for lane width. Our shoulder width is wider at 8 feet than the assumed 6 foot. Side slope is a little steeper at 1 to 6 than the 1 to 7 assumed for baseline conditions, and the baseline condition for median width is 30 feet. So first step, we would calculate our predicted crashes for this length of highway segment using our SPF equation. We would then use the A and B coefficients for divided highways, and we predict about 28.01 crashes per year. The math's fairly simple and straightforward. The power of the results are big. Now, applying crash modification factors, we can adjust our predicted crash performance, our prediction of crash frequency, to the conditions that actually exist for our segment, where they differ from the assumed baseline conditions. In the case for lane width, we had an 11-foot lane, and we're above 2,000 ADT, so our example is our 11-foot lane, and we're above 2,000 ADT, so our adjustment factor would be 1.03. we need to account for the distribution of crashes, just as we did in undivided highways. That lane width only affects cross-section related crashes and not total crashes. So adjusting to WRPE in terms of total crashes, the value is 50% rather than 0.27 for rural two-lane highways. And we do the math, and we end up with a AMF, a CMF that is, for lane width of 1.015 or 1.5%. For shoulder width, and we had an 8-foot shoulder, so the adjustment is straightforward, and we just use the value off of table 11-17.